Let's look at some more homework problems from section 6.3. Number 17, again, we want to solve the differential equation and then find the specific solution using the ordered pair provided. So first step, y prime gets replaced, rewritten as dy over dx. Separation of variables, so we're going to begin working to get the y's on the left and the x's on the right. So initially, I'm just going to add the x parentheses 1 plus y squared to the right side. And we can divide out the 1 plus x squared to the right, multiply both sides by dx to move to the right. And then this 1 plus y squared, we move to the left. So just using a series of addition, subtraction, and also multiplication, division, we can rearrange so we can have the setup in order for us to take the integral. So the integral of the left, the integral on the right, we're going to have to go through u substitution in both cases. So we let the u value be denominators in both cases. So on the left side, u is 1 plus y squared. Du over dy is 2y. Solve for dy, and we get du over 2y. On the left side, u is 1 plus x squared. The derivative is 2x. And so after you cross multiply solve for dx, you get du over 2x. We make our substitutions. The denominator gets replaced with u on the left side. Dx is du over 2y. We see that the y's cancel out, pull the 1/2 out, and we look at the remaining integrand, and we see we do have a rule for that. This is natural log rule. So we get 1/2 natural log of absolute value of 1 plus y squared. On the right side as well, same thing, substitution, but now the denominator for 1 plus x squared gets replaced with u. Dx is du over 2x, so very similar to the left side. The 1/2 gets pulled out. We get natural log of u, so 1/2 natural log of 1 plus x squared plus c. These equations both have 1/2. I can multiply everything through by 2 to get rid of this coefficient. So we have natural log of 1 plus y squared is equal to natural log of 1 plus x squared plus c. We want to solve for y. We want to get this expression out from under this natural log function. So we're going to exponentiate both sides. And the left side, which is going to be a clean drop, the natural log will drop to be 1 plus y squared. On the right side, we have to first rewrite it as e to the natural log of 1 plus x squared times e to the c. We want to be able to pull out that constant. Once we pull out that constant, this expression e to the ln will drop out, leaving us with just 1 plus x squared. We can pull the coefficient in front. So we have 1 plus y squared is equal to c times 1 plus x squared. We use the ordered pair now available to us so that we can solve for c. Plug 0 in for x. Plug root 3 in for y. And next, we're going to have 1 plus root 3 squared, which is simply 1 plus 3, is equal to c times 1 plus 0 squared. So that's just going to be equal to c. So my c value is equal to 4. So now we're getting closer to our specific solution. 1 plus y squared is equal to 4 times 1 plus x squared. We still need to solve for y, so step by step, we're going to subtract 1 from both sides. I'm going to distribute the 4 through on the right. Combine like terms, 3 plus 4 x squared. Take the square root of both sides, so y is equal to plus or minus square root of 3 plus 4x squared. And again, we're left with two separate functions. We have to decide which one satisfies the ordered pair 0, root 3. So we test both of them, and we see that it's going to be the positive one that will hold true for this ordered pair. So y is equal to, our specific solution is therefore positive square root of 3 plus 4x squared. All right, let's look at 19. 19, du over dv is equal to uv sine of v squared, and the ordered pair is at 0, 1. So in this case, we're going to get the u's on the left and the v's on the right. So after we move some terms around, we have du over u, and the right side is v sine of v squared dv. Left side is simply going to be the log rule, so natural log of the absolute value of u. On the right side, we have to do a little bit more work. We don't have any rule for v sine of v squared, so we have to look at u substitution. So we let the u value be what's inside the parentheses, v squared. So our derivative is 2v. Solve for dv, we get du over 2v. And we get the integral of v times sine u over dv over 2v. Sorry, dv over 2v. The v's cancel out. We pull the 1/2 out. And 1/2 times the integral of sine of u is simply negative 1/2 cosine of u. And we make our substitution. Plug in v squared back for u. And now we can solve for u. Take exponentiate both sides. So e to the natural log of u is simply just going to be u. And e to the negative 1/2 cosine v squared plus c, we can split this up into e to the negative cosine v squared times e to the c. E to the c is simply a constant. We can pull that constant out in front. So now we have our general solution. We can plug 0 in for v and 1 in for u. So when we do that, we get 1 is equal to c times e to the negative 1/2 cosine 0 squared. Cosine of 0 is simply 1. E to the negative 1/2 is simply e to the 1/2 in the denominator. We can cross multiply, solve for c. C is equal to e to the 1/2. So now we can plug e to the 1/2 in for c in our general solution, and we get u is equal to e to the 1/2 times e to the negative 1/2 cosine v squared. We can further simplify because this is the product of two like bases, so then we can just add the exponents together. So e to the 1/2 minus 1/2 cosine of v squared is equal to u. All right, one more problem here. This is 21 from section 6.3. We have dp minus k dt, kp dt is equal to 0. And we're given the ordered pair 0, p sub 0. So we're going to start separating the variables. The p's on the left, everything else on the right. So add the kp dt to the right side, divide both sides by p. So now we have a variable separated, dp over p equals k dt. Take the integral of both sides. The left side will just be natural log of u. In this case, our u value is p. On the right side, we have a constant. So integral of a constant is constant times a variable plus c. Exponentiate both sides. E to the ln of p will simply give us p. E to the kt plus c, we can think of it as e to the kt times e to the c. E to the c is a constant. Pull the constant in front. Now we can plug in our ordered pair to find our specific solution, to solve for c. So plug 0 in for t and p sub 0 in for p. So we have e to the k times 0, which is going to be e to the 0, which is 1. So c is equal to p sub 0. And then replace c with p sub 0. So p is equal to p sub 0 e to the kt.